This module will focus on a special type of prediction model known as a neural network. Neural networks, in one form or another, have helped to revolutionize applications of artificial intelligence due to their often high performance in a range of different prediction tasks. Neural networks are a type of nonlinear model. While we've learned about linear and logistic regression methods can help model linear relationships in data, neural networks can model more complex nonlinear relationships and require few to no assumptions to be met in order to do so. These models are sometimes called universal function approximators for their ability to model virtually any functional relationship with sufficient complexity. There are many different variants of neural network model, some of which we will cover in this module, but they are all based on the same fundamental structures. Some of these variants, for example, are better suited for handling certain types of data, such as images or sequential sequences. Other types of models are certainly still quite common for a range of prediction tasks, like regression models, decision trees, SVMs, etc. But neural networks have become a powerful tool that has led to many advancements in a range of fields, including education. Much like linear regression models, neural networks are also based on regression. They're usually depicted using a notation of interconnected nodes, which we will look at later, and these nodes are arranged in layers, with the number of layers describing the depth of the model. This has led to the term deep learning being used to describe areas where they are applied. Before diving into the complexities of neural networks, let's start by taking a deeper look at linear regression models. Specifically, let's consider how a linear regression model is trained. That is, given a set of data, how do we identify the line of best fit to that data set? How do we fit this line function? To illustrate this, let's consider this hypothetical set of points. We have a student study time along the x-axis and their corresponding scores on some assignment or some assessment along the y-axis. If we want to find the line of best fit, we can first start by drawing a random line somewhere on our data. Perhaps we draw a horizontal line here. Visually, we can see that the line doesn't quite fit the data very well. We have some data points very close to the line, but others are much farther away. We can calculate a measure of error for this line by taking the absolute value difference of each point and the corresponding point on the line and summing these values together. We could even plot this value, if we wanted, with the corresponding slope of the line. So when we have a slope of 0, we are left with this particular error point. From here, we can now try a different value of m, our slope, or the coefficient of our line. If we rotate our line a little, we might find that our error decreased slightly. And we can keep doing this over and over until we find where a lower bound emerges in the plot of error. And the line of best fit is the slope corresponding to the lowest error with respect to the data points. In the case of linear regression, we will always end up with what's called a global minima. That is, we will always have a point where the error is lowest in this particular cost function. Functionally, we could skip this iterative process and instead find where the error function's derivative equals 0, and then solve for our coefficient. And this would work whether we have one feature, where we're trying to find one slope or one coefficient, or if we have 100 features, each with its own coefficient. Neural networks, on the other hand, may not have a global minima, as we will look at in a later video, and instead will require us to train them iteratively as it regresses on the data to find the function of best fit. With that, let's finally cover some notation before continuing further in this module. It was described earlier that neural networks are typically visualized as sets of nodes and layers, but it is often not recognized just how closely related they are to linear regression models. If we take a linear function, such as the one we see here, we can make some alterations while keeping the same form. For example, we could change the variable used to represent the slope, or coefficient, and instead refer to these relationships as weights, represented as W here. despite having made no tangible difference in the representation. We're just renaming that variable to be a weight rather than a slope or a coefficient. We could also recognize that we often have multiple predictors in our model, and each would have its own coefficient, or weight, that is learned along with an intercept. Again, we still have our linear model here. We have made no tangible differences. We've just changed a little bit of the functional form. So we can represent this model using nodes and layers by reformulating each component to what we see now on the left. We still have our features, along with an intercept along the bottom here, represented as these blue nodes, with a node at the top representing our dependent variable y. The lines connecting each feature to the dependent variable represents the set of weights or coefficients that describe the relationship between each predictor and the dependent variable. In this way, the representation on the left is just a different way of visualizing the equation on the right. If we look at a logistic regression, we are effectively just taking our linear model and applying a logit function. We can represent this in our visualization by adding a sigmoidal shape, that little s, to our dependent variable node to indicate that a function is being applied to the input. In the case of neural networks, this function is called an activation function, and we'll see that there are others that are also commonly applied beyond this type of sigmoidal shape. We can extend this notation to neural networks by just adding additional nodes and layers. However, the interpretation of each of the nodes and weights within the representation all maintain the same definition within our model. It is just the activation functions combined with the propagation of data through the multiple layers of these models that then allows the model to learn more nonlinear functions and more complex functions with each layer.